Welcome to This Explainer. I'm absolutely thrilled to have you here today because we're going to unpack one of the most revolutionary ideas in the entire history of science. We're looking at John Dalton's 19th century atomic theory. We'll explore its foundations, its core features, and yeah, even its fundamental flaws. This is the theory that literally built the modern world of chemistry. So let's jump right in. So what is everything around us actually made of? It's the ultimate question, isn't it? Now, before Dalton came along, the idea of atoms was, well, purely philosophical speculation. You had ancient Greek thinkers like Democritus just sitting around pondering this stuff. They guessed that if you kept cutting something up, eventually you'd hit an uncuttable piece. But they had absolutely no proof. It was a really cool philosophical concept, but it wasn't science. You couldn't measure it, test it, or, build an industry on it.
Section 1. The birth of modern chemistry.
Right at the dawn of the early 19th century, this English scientist named John Dalton steps onto the stage. And Dalton, he was the ultimate catalyst. He didn't just ponder the universe, he actually measured it. He took all that ancient philosophical speculation and transformed it into a modern, experiment-based scientific theory. By doing this, he laid the exact groundwork for scientists to finally understand matter at its most fundamental level.
Okay, let's dive into this. Section 2, Laws that built the theory. You see, Dalton didn't just wake up and guess how the universe worked. He built his theory on established experimental laws. The very first critical building block came from Antoine Lavoisier. The law of conservation of mass simply states that matter cannot be created or destroyed in a chemical reaction. Think about it. If you start with exactly 10 grams of material in a closed reaction, you're going to end up with exactly 10 grams of material. The total mass is perfectly preserved. It's a fundamental rule of the universe that gave Dalton a really rigid framework to operate within. Moving smoothly along, we have Joseph Proust's law of definite proportions. This rule dictates that a compound always contains the exact same elements in fixed proportions by mass. It means nature is incredibly consistent. Water is never just some random mix of hydrogen and oxygen. It locks together in highly predictable, fixed proportions every single time. And then we get Dalton's own mathematical addition, the law of multiple proportions. He figured out that when two elements form more than one compound, the ratios of their masses are always simple whole numbers. No messy fractions. It's perfectly clean. And this realization, this was the spark. It finally inspired him to propose a structured, overarching explanation of matter. If matter always combines in these perfect whole numbers, well, matter itself must be made of whole, individual pieces.
Section 3. Dalton's 6 postulates.
Let's rapidly walk through his first 4 rules, really building that mental picture of these unique, indestructible atomic building blocks. Postulate 1. Matter is made of tiny, indivisible atoms. 2. Atoms are completely indestructible. 3. Atoms of a given element are entirely identical to each other. Every single oxygen atom in the universe is exactly the same. And 4. Different elements have totally unique atoms. An oxygen atom is fundamentally different from a hydrogen atom.
Now, what's really interesting about this slide is exactly that 2-to-1 ratio you see. This perfectly illustrates postulate 5. Atoms combine in simple whole number ratios. Just like at water, H2O. It's exactly 2 parts hydrogen to 1 part oxygen. They lock together like perfectly sized puzzle pieces to form compounds.
To wrap up the postulates, we have rule number 6. Chemical reactions don't create new matter out of thin air. And they don't destroy it. They simply involve the reorganization of atoms. Basically, a chemical reaction is just the shuffling and rearranging of these eternal atomic pieces into new combinations. Simple, elegant, and completely groundbreaking.
Section 4. The billiard ball mall.
This is the most famous visual metaphor of Dalton's work. He imagined atoms as solid, hard, completely indivisible spheres, lacking any internal structure whatsoever. Seriously, picture tiny, perfect billiard balls. It's a beautiful model that made the math work perfectly and gave scientists a really tangible way to finally visualize the microscopic world.
Section 5. Breaking the billiard ball.
But science never stands still. And this brilliantly illustrates exactly where Dalton's rigid 19th century rules hit a wall against our modern subatomic reality. While his idea demanded indivisible, identical atoms, we now know about subatomic particles, and where he confidently stated that all atoms of the same element are completely identical, modern science proved that isotopes exist.
Let's break those modern discoveries down just a bit more. First, J.J. Thomson discovers the electron, completely shattering that billiard ball idea. Then, protons and neutrons are found inside. We discover isotopes like carbon-12 and 14, proving atoms of the same element absolutely can have different masses. Oh, and for the ultimate plot twist, nuclear fission and fusion prove that atoms actually can be destroyed. Sorry, Dalton, but that totally contradicts the rule of eternal indestructibility.
Section 6. Dalton's lasting legacy.
So despite those historical inaccuracies, why is this still the starting point of modern chemistry? Well, let's review his merits versus his limitations. Yes, he had massive blind spots regarding internal structure and chemical bonding. But on the flip side, look at the merits. His work laid the undeniable foundation for all the later, more accurate atomic models from folks like Bohr and Rutherford. And it created the absolute basis for stoichiometry, the actual math that lets us calculate chemical reactions.
And those very foundations paved the exact path for the practical applications we rely on today. His quantitative approach is what drives massive chemical industries. It's the basis of modern pharmaceuticals, allowing us to synthesize medicines with exact precision. It drives cutting-edge material science. His rules might have been a bit oversimplified, but they were right enough to build our entire industrial society.
Science is a constant evolution of breaking and rebuilding. Dalton took philosophy and turned it into science, and then later, scientists cracked his billiard balls wide open to reveal the quantum realm. So I want to leave you with this to think about. Based on everything we just explored, which widely accepted, rock-solid scientific theory of our modern era do you think will be completely shattered and rewritten in the next 100 years? Keep questioning, keep learning, and thank you so much for joining me on this explainer.